This story begins not in a modern laboratory, but in the fragile workshops of the 19th century. For centuries, human civilization relied on glass and pottery to carry liquids. Glass was clean and reliable, but it was heavy, expensive to transport, and notoriously delicate. A single stumble could shatter an entire day's work and waste valuable liquids. People accepted this as an inevitable law of nature. If you wanted to store water, medicine, or milk, you had to accept the weight and the risk of broken glass. No one imagined that the world would one day hold its liquids in an entirely artificial, remarkably durable shell. But human curiosity has always been driven by the search for convenience. In the mid-19th century, inventors began experimenting with early synthetic compounds to replace natural materials like ivory and rubber. In 1907, a Belgian chemist named Leo Baekeland created Bakelite, the first fully synthetic plastic. It could be molded under heat and pressure, and once cured, it remained rigid and resistant to heat. Soon, synthetic polymers began appearing in products that had traditionally been made from materials such as wood, metal, and glass. Yet, for decades, no one thought of using this new material to hold ordinary beverages. Liquids required a container that was not only flexible and durable, but completely non-toxic and capable of holding intense pressure. As decades passed, plastic expanded into toys, car parts, and packaging, but the beverage industry remained locked in the era of heavy glass bottles. In the mid-20th century, early plastic containers made of polyethylene appeared for cleaning products, but carbonated beverages presented a difficult challenge. Carbon dioxide could gradually diffuse through the polymer, making it difficult to preserve carbonation for long periods, while internal pressure could also cause deformation in containers that were not designed for it. For a long time, manufacturers believed that carbonated drinks and many other beverages were best kept in glass or metal containers. Today, many people believe that modern plastic bottles were just a minor variation of ordinary plastic wrap or industrial polyethylene. But the truth is entirely different. The plastic bottle we know today required a breakthrough in chemical engineering that took decades to master. It began with a specific polymer known as polyethylene terephthalate, or PET. Created in 1941 by British chemists John Rex Winfield and James Tennant Dixon, PET was originally developed for synthetic textile fibers. It was later used commercially in polyester fibers such as Dacron. On a microscopic level, PET is made of long polymer chains containing carbon, hydrogen, and oxygen. When PET is stretched in two directions during the bottle-making process, its long polymer chains become more highly oriented. This molecular orientation increases the material's strength and improves its resistance to the movement of gases such as carbon dioxide. The result is a material that can remain lightweight and transparent while becoming strong enough to withstand the pressure inside carbonated beverages. Yet having the right chemical compound was not enough. You still had to find a way to mass-produce hollow, thin-walled bottles at industrial scale without tearing the plastic. Throughout the 1960s, engineers around the world struggled with this problem. Blow molding existed, but attempts to form PET into large, thin containers could result in deformed or uneven bottles that lacked the strength needed for pressurized beverages. If a hollow plastic container was so difficult to manufacture at scale, could it ever replace glass? That was the question facing an engineer named Nathaniel Wyeth at the DuPont Chemical Company in the late 1960s. Wyeth was not a packaging marketer or a corporate executive. He was an inventive mechanical engineer who noticed how fragile glass soda bottles were during shipment. He wondered why a lightweight, tough plastic could not be inflated like a balloon into a permanent mold. Colleagues told him it was impossible because heated PET could tear instead of expanding evenly. Wyeth refused to accept that limitation. For years, Wyeth and his colleagues conducted experiment after experiment. Early test preforms collapsed, melted, or expanded unevenly. But in the early 1970s, Wyeth and his colleagues developed and patented a stretch blow-molded PET bottle. By mechanically stretching a heated test tube-shaped preform with an internal rod. While forcing high-pressure air into it, they could orient the polymer and cool it against the mold walls. This produced a lightweight bottle with dramatically greater strength and impact resistance than conventional glass containers. That single invention did not just create a new container, it ignited a global packaging revolution. In 1977, PET beverage bottles entered the commercial market in the United States. Beverage companies such as Pepsi and Coca-Cola quickly recognized the enormous advantages of PET. A glass bottle accounted for a massive portion of the total shipping weight of a beverage crate. A PET bottle weighed only a fraction of that. The dramatic reduction in packaging weight could lower transportation costs and energy use, while dramatically reducing breakage during transport. Production lines could also manufacture thousands of bottles per hour. Soon, the entire global distribution system reorganized around the disposable plastic bottle. Supermarkets expanded, vending machines spread across every continent, and bottled mineral water, a product that once seemed absurd to pay for, became a multi-billion-dollar global commodity. The plastic bottle also made packaged drinking water easier to transport into disaster zones, remote hospitals, and regions where reliable municipal water was unavailable. What was once an expensive luxury became one of the most ubiquitous forms of consumer packaging on Earth. But the story of the plastic bottle didn't end when it conquered the world. In many ways, that was only the beginning. The same characteristics that made PET such an extraordinary material also created a problem that no engineer in the 1970s could have fully predicted. The bottle was designed to survive the journey from factory to store, from store to home, and from home to wherever the consumer finished drinking. But the useful life of the liquid inside the bottle could last only minutes, while the material itself could remain in the environment for generations. And this created one of the strangest contradictions in modern manufacturing. A container designed to be used for a few minutes was made from a material designed to last far longer. Today, plastic bottles are everywhere. They are found in supermarkets, airports, schools, offices, sporting events, hospitals, construction sites, and emergency relief operations. In many parts of the world, they provide something genuinely important: access to packaged drinking water when local supplies are contaminated, damaged, or unavailable. That is why the story is more complicated than simply saying that plastic bottles are good or bad. The bottle solved a real engineering problem. It reduced weight, it reduced breakage, it made transportation more efficient, it allowed manufacturers to move enormous quantities of liquids across long distances at a cost that glass could never match. But once billions of people began using the same disposable system every day, the mathematics changed. A single bottle is almost meaningless. A billion bottles are not. And today, humanity produces hundreds of millions of tons of plastic waste every year. The United Nations Environment Program estimates that the world generated around 400 million tons of plastic waste in 2024 alone. Much of that waste does not simply disappear. Plastic can fragment into smaller and smaller pieces, eventually becoming microplastics that can move through rivers, oceans, soil, and ecosystems. This has changed the question engineers are asking. For much of the 20th century, the question was, how can we make a better plastic bottle? Today, an equally important question is, what happens to the bottle after we are finished with it? One possible answer is recycling. PET has an important advantage over many other plastics. It can be collected, processed, and transformed into recycled PET, often called rPET. Instead of beginning again with newly produced plastic, manufacturers can use recovered material to create new packaging or other products. But recycling is not as simple as throwing every bottle into a recycling bin. The bottle has to be collected. It has to be sorted from other materials. Labels, caps, colors, contamination, and different types of plastic can complicate the process. The material must then be cleaned, processed, and converted into something that can be used again. That means the future of the plastic bottle is not determined only inside a chemical factory. it is also determined by what happens after a person finishes drinking from it. And this is why governments, scientists, manufacturers, and environmental organizations around the world are increasingly talking about something called a circular economy. The idea is simple. Instead of making a product, using it once and throwing it away, the goal is to design materials and systems in which products remain useful for as long as possible. That can mean recycling bottles into new materials. It can mean increasing the use of recycled PET. It can mean reducing unnecessary packaging. And in some situations, it can mean replacing disposable containers with refillable systems. The debate has now become global. In 2025, countries gathered under the United Nations process to negotiate a legally binding international agreement aimed at addressing plastic pollution. The negotiations ended without a final consensus, showing just how difficult the problem has become. In 2026, the international process continued under new leadership. In February, countries elected Chilean Ambassador Julio Cordano as the new chair of the negotiations, while preparations continued for the next substantive stage of the process. And perhaps that is the most fascinating part of the entire history of the plastic bottle. It was never created to become one of the symbols of the environmental crisis. It was created to solve a problem. Glass was heavy. Glass broke. Transportation was expensive. Engineers wanted something lighter, stronger, and cheaper, and they succeeded. Perhaps too well. The plastic bottle is a perfect example of how technological progress can create consequences that appear only after the technology has been adopted on a massive scale. The invention itself was not simply a failure, it was a remarkable engineering achievement. The real challenge came afterward, when billions of people began using that achievement every single day. More than half a century after the first commercial PET bottles appeared, the world is still living with the consequences of that breakthrough. The question is no longer whether humanity can make a bottle that is light, transparent, strong, and inexpensive. We already know how to do that. The question now is whether we can create a system in which that bottle does not have to become waste after its first and only journey. Because perhaps the next great revolution in the history of the plastic bottle will not be the invention of a new material. It will be the invention of a better relationship between the material we create, the products we use, and the world we leave behind. And that is the strange legacy of the plastic bottle. Humanity spent more than a century trying to create a container that would never break. Now the challenge is learning what to do with a container that refuses to disappear.